And I received emails about the lecture recording. Sorry, I didn't get a chance to upload the recording properly for the last few lectures. I'm working on it. Uh, I compiled mostly everything, and I'll upload it after class today when I go back to my office. Yes, I'm sorry. Oh no, so you have a final exam, right? You have a final exam. The project has a specific percentage, and you'll find that on the syllabus that I uploaded, right? So it has a small percentage, not small. It is a very important percentage. So don't miss the project. This is a new addition to this course, and I actually added a few things that are new for this course, which is I think absolutely critical, because I recommend, and please read my announcement. I don't typically post anything unless it is important. So what I will do is I'll emphasize, how you should approach the project. I understand the first time you read it, it will probably be overwhelming in a way that you feel like, oh, how do we do it? I want you to go through it, think about it for about a week. And again, I'm going to post about it, but just to quickly tell you what to expect. And then try to come up with an approach as to how we will handle this. How will you incorporate the system I wanted to incorporate? So you'll be essentially making a voting machine. Okay. So, right. How can you do it? And after a week, I will collect some responses from you and I will give you extra credit for whoever submits that report. Report in a sense that extra credit, if you don't need it, it's fine. If you already have perfect grade and you think you're going to do well in the finals, it's not a problem. You don't need to do it. You can just do and get the final project done and you don't have to worry about it. But if you show me your thought process after about a week, within a week, then I can review that and I can give you some extra credit for it. I'll mention this in detail. And then I plan to help you because I know it's a little bit challenging, but I want to see your responses and see how you approach it. That's what I want to figure out, right? And that's what I want you guys to figure out yourself. Like, how much do you really know about digital design, right? Because only when you do a real life project, you see whether or not you can consolidate your learning with something real life. Okay. So anyways, without further ado, let me post that announcement and then I'll be happy to answer questions on Friday. Yes. Oh, I'll give you a week. It's not really that much of a formal report. I want to see some specific steps, even if it is bullet points or something like that, or a flow chart, that's fine too. I'll mention specifically what I expect from you guys. It's a week from today. Yes. So I posted the project today and I'll post the announcement today and I'll give you a week. Yes. Uh, sorry. So I forgot to talk about the quiz. So there is oh yes. So I just realized. Thank you for reminding. My bad. Uh, I don't know. I somehow keep mixing these dates. So let me not rush this. I will post a new date and work with you all. I already mentioned that the syllabus was going to be on sequential logic. It is going to be on sequential logic, but since I didn't give you any heads up or something like that, I'll push it to a later date, right? I'll give you some time to prepare. So thank you for reminding. Anyways, any other questions or comments? Okay. All right. Thank you. So here is where we were in the last class. We were discussing the setup time constraint. And I told you there are two constraints that determine the overall working principle and performance metrics for sequential logic. Setup time constraint is the first of those two. Okay. So we learned about the propagation delay of a flip-flop, the time it takes for you to get the input to the output after the clock appears. So we measure everything from the clock edge, right? So it can also be mentioned as clock to Q delay, or you could simply call it propagation delay for flip-flop, PFF. Okay, now for combinational logic, there is no clock, so there is no clock to Q delay. We simply call it propagation delay. So TP, propagation delay for combinational logic. So TP com. And I told you there are two specific time parameters available for flip-flops, setup time and hold time. So your data needs to appear before the clock edge well ahead of time. There is a specific time window within which you cannot have any kind of input changing. So imagine if this is your clock signal, there is a time window before it within which you cannot handle any kind of input changes. So your input, whatever it needs to do, should finish doing before this setup time. Yeah. And similarly, this is setup time. After the clock edge appears, the flip-flop cannot handle any more changes to the input. So you have to give it some time to settle down, no matter what it is. Even if you want to change it, you have to wait, let it stabilize itself, and then change it. So this is called hold time. So you basically have to hold onto whatever activity you want to do for this time period. So setup time and hold time. Setup time appears before the clock edge, and hold time appears after the clock edge, just so you know. So now we saw an example where we were driving a flip-flop B, and we are pushing some data from point P to point Q to point R all the way to S. So we are trying to push a bit of information from left to right through a flip-flop and combinational logic all the way to the second flip-flop. Okay. Now, notice, let's try to calculate the delays from P all the way to the final output S. So first, you have to go through the first flip-flop A. So you have to encounter the propagation delay for flip-flop A, TPFFA. And then once it comes down to Q from P, it has to go through the combinational logic. So there will be an additional delay, which is TP combination, right? So at this point, the data is here at input R. But I told you that the data must appear, if you want to handle the data properly, it must appear before a certain time. And that certain time is determined by, let's take a look at the clock signal. This is the clock edge. Will the setup time be on the left or right? On the left. So this is your setup time, say. So your data must appear before this time period. Are you guys all good so far? Okay, and finally, you can now allow the clock signal after the setup time. So this is basically operating exactly at the edge. Okay, now, if you add up all these numbers, what you get is TPFFA, which is this one, plus TP combination, plus this setup time. This is the time window you need for flip-flop B to properly operate. So you cannot activate flip-flop B. Let's consider that this is where your counter starts, your time clock starts. Okay? You cannot let the next clock cycle come before this time period. You guys all agree with it? And I asked you a question in the last class, and in the middle we digressed. So I asked you what happens when the clock edge appears here. If the clock edge appears here, the problem would be you'll be within the setup time. So you'll not give flip-flop A enough time to set up, right? So that will be a failure. First of all, your flip-flop may or may not eventually get the right number, but you simply cannot trust it. So that's the problem. You have to eventually reset the system and restart. That's what we don't want to do. Okay. And then I asked you another question, which was, what happens the clock appears later, like right here, for example? Will there be any problem with that? Will your system fail? First question is, will your system fail? No. You have given, so if I need 10 seconds to set up, you give me 20 seconds. Is that bad? No, I need 10 seconds to get ready, but you give me 20. It's fine. So yeah, sure. As long as the clock comes after this time, it's not going to be a challenge. So that's why the constraint says the time period of the clock. How do you define the time period of the clock? The difference between similar edges, rising edge, or falling edge, right? Consecutive edges. So this is the time period of the clock. The time period of the clock has to be greater or equal to this total time. Does that make sense? This is the equation for setup time constant. This is what you get when you read a textbook or something that talks about setup time constant. This is an equation. It doesn't come as a random equation per se. It comes from the practical consideration of the system. Does that make sense, folks? So that means if your time period of the clock is higher, it is better for setup time because you give the system enough time to stabilize. Okay. Now, in terms of functionality, there will not be any challenges. But if I ask you, do you see any other? So there are two challenges: functionality and performance. In terms of functionality, as long as your clock edge appears later than it should, it is fine. But if it appears sooner than it should, it will not be okay for the functionality. Okay. All right. However, for performance, do you think it is okay to delay the clock? Okay, by delaying the clock edge, I mean your time period will increase. So frequency, operating frequency is actually inverse of time period, as you know. If your time period increases, your frequency of operation will go down. So for example, if you try to buy a processor for your laptop, will you go for 1 gigahertz or 2 gigahertz or 4 gigahertz? The higher the frequency, the better it is because you can handle more data faster, of course, right? So imagine this time period is not just a time window. This is going to determine the clock frequency of your overall system. So if you increase it 10%, you have a significant performance reduction in your frequency. So you don't want that. It is not just one flip-flop operation that you're saving because you cannot randomly change the time period. Once you set a time period, that's it. It is repeated. It is a periodic function, right? So it is repeated. So if you increase it by 10%, it is 10% all the time. So you see, it's not an easy thing to say that we are just going to give it more time than it needs and be safe. So we often operate at the very edge to make sure you get the best performance out of the system without leading to failure. So ideally, we'd love to do this. Time period exactly equal to this one. Obviously, nothing is perfect. So if you make it exactly equal, it will fail. So you have to keep some margin. Okay. Now, first of all, I'm telling you already here that you have to keep some margin. You have to delay the clock a little bit, but not too much. If you delay it too much, the performance will be hard. Yes.
Standard for like industry.
That's a great question. They will never tell you. It's a trade secret, right? So when we teach in class, we use random numbers like 10 nanosecond, 5 nanosecond, 20 nanosecond. We make them up. Okay. So for industry, they design these chips in a way that you cannot even get into that level of measurement. When you try to open up the system and try to measure it, it is almost like you see Mission Impossible movies where the message self-destructs itself. So they don't blow up or anything. They basically mess up the overall circuit. It will never work. So this is by design, because otherwise one company will buy some other company's chip and reverse engineer and fast forward 10 years of research. So for example, Intel is doing research on some technology for 10 years, and some other company can just buy one of the chips from the market and just reverse engineer. Oh, this is what their numbers are. And they can also report if your numbers are not as good as the other competitor, then your stock prices will go down if they could report it. Okay. So oftentimes you can cover your hardware weakness with software. So there is a software hardware interplay. Apple does it. For example, Apple makes their own software. They make their hardware as well. They design their hardware so they can optimize. So now in a given year, if you don't manage to get enough improvement in the hardware, you could try to make it up with software. So people will never know. And people come up with this approach. Now it is public knowledge. We know this. Like 4 cores versus 2 cores versus 7 cores. There was a time when there was just 1 core, single core. And every other year, the frequency will increase. You'll go from few megahertz to 100 megahertz to gigahertz. Gradually, your frequency increases, so speed increases. But at some point, okay, you go from 1 gigahertz to 4 gigahertz, but not by increasing frequency. How do you do it? You, instead of using 1 core, you use 4 cores. So, you basically do 4 times the work, but it appears that it is 4 times the frequency. It is not. The frequency remains the same. Now, if you see the performance metrics, the frequency is flat. And there is a reason. I don't want to go into that tangent, but the frequency is no longer increasing. Okay, that is related to thermal issue. The chip will literally fry itself if you increase the frequency any further. It is generating so much heat. So instead of increasing the frequency, we are increasing the chip. So, but now if I don't tell you, you feel like, hey, Intel was able to quadruple their frequency. No, we didn't. Like if you are another company trying to increase your frequency and your chips are burning out, you tell your engineers, how is Intel doing it? See, they're quadrupling their frequency. Why can't you do it? Right? But if I tell you that we actually didn't, We just quadruple the number of chips. You see my point here, right? You can get a few advantage point by hiding this detail. But this is important that when you join industry, you have to work for them to know their numbers. And then you cannot tell your friends. If you do, they can come after you and there will be a lawsuit. Okay, so you have to be very careful with these numbers. Even if I know, I can tell you. All right. Any other questions? All right. Now, I hope this equation makes sense to us. It's a very simple equation. I don't want to make it appear more important than it is, but it is actually, like I said, extremely important. And towards the end of this lecture, I'll tell you why this is so important in a second. So now you know, just the philosophy of this slide is that your clock cannot be too fast. Do you guys all agree with it? It cannot be too fast. If it is too fast, if it is oscillating too fast, you cannot allow these delays. You cannot allow the data to propagate well in advance to the next flip-flop to let it settle down and set up properly. Okay. Okay, now let's move to the next slide, folks. This is a more detailed view. Please allow me to guide you through it and just observe and pay attention. If you miss it, I'll repeat, but try to focus. So let's see. From P to Q, once the clock edge appears, by the way, we don't care about the setup and hold time for the first clock edge. We are assuming everything is fine. We will only be tracking the next clock edge, okay? Because we don't know the history before it. So to know whether it is doing the right thing or not, we need to know the history before it. We don't know that. So we don't have to take the first clock edge too seriously, but the second one will determine whether things are working or not. So this is the first clock edge. We assume that the data stabilized, which is here, to 1 well in advance. We assume that it is fine. And then when the clock edge appears, P goes to Q. And notice P has gone to Q. This is what kind of delay, folks? Clock to Q delay or propagation delay of the flip-flop. But do you measure it from P to Q, folks? Where do you measure it from? This is going to be one of the MCQs in your final exam. I'll ask you to calculate that. Okay, so now pay attention. Yes. Thank you. Yes, you don't measure it the way I've drawn it here. You don't measure it from P to Q. It doesn't matter that P stabilized 10 seconds, 100 seconds ago, because you don't see that. Your flip-flop only sees the input after the clock edge appears. So whatever happened before, it doesn't matter. So this is your clock to Q delay. Don't take the edge where the input changed. Okay, take where the clock came. So this is also the propagation delay for the flip-flop. Instead of calling clock to Q delay, which is difficult to type, we often use TP, propagation delay for flip-flop. That's it. Okay, now, next. After this appears here, there is no concept of clocking because combinational logic will not have a clock. So you have to go from Q to R and it takes some time, which is the propagation delay for combinational logic. All right? Propagation delay for combinational logic. All right, number 3. You have to make sure that this data arises and sets up properly before the setup time. So who determines the setup? Whose setup time are you looking at? Are you looking at flip-flop A's setup time or flip-flop B's setup time, folks? Tell me. Okay, so where is the data now? Here. And you're looking at flip-flop B. So that's why you see, notice these subtle differences. You're looking at the setup time for flip-flop B because different flip-flops may have different setup times, by the way. So you have to look at, and I will confuse you with numbers. Flip-flop A has 10 nanosecond setup time. Flip-flop B has 20 nanosecond setup time. Which one do you take? You decide accordingly. Okay. And I can go through the chain. There could be a third flip-flop. So when you look at the final output, you look at the setup time for the final flip-flop because that needs the data to be set up. Are you good so far? Okay. Now, so before the setup time, this is setup time. So your data stabilized before the setup time. So you're good. Okay. So now I'm going to ask you a quick question. Just track this red dot here. This red dot marks when your data needs to finish setup. And it has just made it. So it's fine. Deliberately, I'm showing you the exact limit of this activity, right? So you have managed to set it up properly. Let's go to the next slide. And please notice the difference between clock, I'm telling you beforehand, and the final input R and look at these two edges. Let's move to the next slide. What changed? What happened here, folks?
It's too slow.
Yeah. So your transition occurred, instead of occurring here, it occurred a little bit later. But now it occurred during the setup period. Does that make sense? Think about the flip-flop B. Imagine flip-flop B is getting prepared for the clock. It doesn't know that there is a data coming its way. It doesn't know anything. So everything else is being controlled by this combinational logic and the previous flip-flop. It just has to make sure whatever comes my way should come well in advance to the clock. That's what this flip-flop B is, dealing with. Does that make sense? So flip-flop B needs the data before this setup time, but the data appeared during the setup period. Will flip-flop B be able to handle this data or not? No. So this is an invalid situation, right? So now there is a setup time violation. So if I give you some timing diagram and mark the setup time and hold time, and I'm going to do that maybe, by the way. So please pay attention. Can you detect setup time violation and hold time? We haven't been there yet, but you can also detect hold time violation similarly. During the setup time and hold time, you don't, some people make them, there is a time limit for your quizzes. You see, 5 minutes, 10 minutes, 20 minutes, whatever. The reason there is a time limit is because given enough time, anybody will be able to figure out. Okay, you have to. So if you go through the chain like this, blah 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 blah, P to Q and R, at some point you'll figure out the problem. But I think where you should start is look at the setup period, which is this is the setup period, and see whether the input, which is right here, changing during this time. If there is a change in the input, there you go. It's a violation. Don't you think? There cannot be any kind of transition. We don't care what type of phrase, 0 to 1, 1 to 0. There cannot be any type of input transition during the setup period. You need to have absolute constant value. Does that make sense, folks? Let's go back to the previous slide. This is your setup period. Nothing's changing. Okay. What happens when the input changes here? Is that good or bad? It is actually good that it is giving you more time. It's fine. But if the moment it goes beyond this limit, done. You have a problem. So notice for MCQs or quick situations like this, you don't have to track all these waveforms, even though I give you all of them. You just need to see during setup time and hold time whether something changed. Yeah. All right. Okay. All right. Now, I'm going to ask you another question here with the violation. Let's see. All right. Now, tell me, if I see that my system is getting a setup time violation, who will I blame for this? Will I blame flip-flop B for it? Flip-flop B? Flip-flop B has nothing to do with it. It just got the data late. Who can I blame for the data to arrive later? Thank you. I can definitely blame the combinational logic because it took too much time to send Q to R. Okay. Do you remember that there was a lecture about multi-stage logic that we did? You can have a logic implemented in 2 stages, 3 stages. Did I tell you that if you have multiple stages, there will be more delay? Every stage adds more delay. So if you could reduce everything to lower number of stages, you reduce the delay. So if you see that this is the problem, you can then go back and reorganize your combinational logic and reduce some stages to reduce the delay. Okay, there is one other guy who can be blamed. That is flip-flop A. Flip-flop A might also take some time. But remember, typically, flip-flop delays are kind of standard. You cannot really do much about them. They're like standardized cells. But combinational logic can be reorganized, rearranged, okay, rechanneled. Instead of having one channel, you can have multiple channels to somehow make up for this delay. Or the other approach would be to just delay the clock. Just delay the clock, like push it a little bit. Okay, one or the other. You don't like to delay the clock. So you like to work with the combinational logic. So you go back and try to optimize the combinational logic. Okay, I will get back to this point towards the end of this lecture. Okay, let's move on to the next slide. and I introduced the concept of clock skew. You didn't ask me this question, but I hope by the end of this semester, you'll get into the habit of this, asking questions. That is, okay, so you are driving multiple flip-flops in the same clock. Nothing is perfect in the world. So you can never have both of the flip-flops get the clock exactly at the same time. It's not just things being perfect, it's also practicality, right? I told you that we need a metal wire to connect clock A and clock B. And anywhere, uh, maybe I didn't tell you that, but if you take 433, there is a lecture on interconnect parasitics. Interconnect. When you draw a metal line, essentially the way you see, for your circuit design, it's like a line. For practicality, it is like resistors, capacitors, resistors, capacitor. It's an RC network. Does that make sense, folks? So any metal line will have capacitors. Can anybody tell me why? I know I didn't teach you this, but you're not supposed to know. It will be a pleasant surprise if you know this. Yes, it is not, but that's an interesting perspective. Any other thoughts? Let me show you. Did I show you in a video that when you design chips, there are multiple levels of interconnect? Did I show you that? Is there just one level or no? There are 11 to even more levels of metals, one going after the other. How do you make sure, do they float in the air? How will these metals be on the chip, folks, on top of other, one on top of other? How will they stay on top of each other so that they don't get shorted out, right? If you just put them on top of each other, they will just get shorted. How do you make sure? What will you do as an engineer? What will you put in between? Yes. Thank you. Yes, perfect. You even gave me the right name of the material. It's called a dielectric material or an insulator per se, which is typically an oxide. Could be silicon oxide, could be other oxide. We often use low-K oxide, but it has to be an insulator, an oxide. Folks, high school physics. If you have a metal insulator, metal, what is that structure? It's a capacitor. It's a parallel plate capacitor, right? So when you draw a metal line, essentially it is not flying. It's not a Superman or something, right? It is staying on top of an insulator, and underneath there is another metal. So there are capacitors everywhere. So if you draw a line, there is capacitors. Okay. So an RC network can never do anything instantaneously. There is a charging process, gradual charging process involved in it. So when you go from this clock to the next clock, there will always be a delay. It's not just you have a lousy circuit design, it is just practicality. Anytime there are two nodes, there will be a delay between these two nodes because there is RC. Are you all with me? The delay could be small or large, depending on how far out they are, but there will be some delay. Now, notice, just take a look at this waveform, folks. Clock A and clock B. So far, we just had one clock. I didn't show you clock A and clock B because they were driven by the same clock. But now we are being more practical. For flip-flop A, you have a clock. Flip-flop B, you have a delayed clock because we are assuming the clock is coming from left to right. Right? So clock A gets the, flip-flop A gets the clock first and flip-flop B will get the clock next. So there is a delay. Do you see this delay, folks? This delay marked as delta is called clock skew between neighboring flip-flops. Like clock delay between. The other name is clock delay. Skew sounds more fancy. So use clock skew so that your cousins cannot understand easily. You see my point here? Engineers always try to make up terms that sounds more fancy than they need to be. It's essentially a delay. You don't get the clock at the same time. The farther out you are from the source, the higher the delay will be eventually. That's called clock skew. Now let's see. We are being more practical gradually, right? So now you have clock A and clock B. I'm drawing the exact same steps, same circuit, going from P to Q, Q to R, and then eventually R to S. Okay, the same circuit. So nothing changes here. The only thing that changed is clock A and clock B. But so if you remove this clock B and check it with the previous slide, you will see the exact same waveform that I've shown you, right? So why am I drawing this? Because I have a question for you again. For flip-flop B, when you decide on the setup time, remember, setup time and hold time are measured from the clock edge. Setup time appears before the clock edge, hold time appears after the clock edge. Did I tell you that? There was just one clock before, so everybody had the same clock edges. But now for flip-flop B, will you look at clock A or clock B? Tell me. When you start measuring the delay, say for flip-flop A, which clock edge do you take? Do you take the edge of clock A or clock B? Which one do you take? A. So when you measure the delay, you measure it from clock A. This is the flip-flop A delay. You ignore clock B. And then combinational logic doesn't have any clock. So you don't even look at the clock anymore. It is just a delay, constant number. And then when you decide on the setup time for flip-flop B, do you look at clock A anymore? Because it gets the clock B as an input, not clock A. So this is the clock edge that you should look at. So there are two red dots for you, just to confuse you. Which one do you take? You take the clock B red dot. That's what defines the setup time. This is your setup time. Okay, so it is easier to confuse you in an quiz or exam with multiple clock. If there is a third flip-flop which has clock C and you're looking at that flip-flop, look at clock C edges, not clock A or clock B. So you have to look at the edges for the corresponding clock because there are so many different clock. Yes.
Okay, why don't you look at the clock edge first, and then whenever the Q edge, and then for clock B, do the opposite. We look at
Yes. Great question. Let me let me repeat that. We discussed this, but that shows that I was not clear enough. First of all, when you calculate the delay appears after the clock has already appeared. So when the clock appears, your input goes to output. So you see after, starting from clock, you go after the clock to Q. Okay, that's why it's called clock to Q. So you start from the clock, go to Q. But setup time, you need to do setup before the clock appears. That's why you go to the left from the clock edge. Yes, this is the setup time. You see this line here, setup time. This is the propagation delay. When you propagate after the clock appears, then you propagate. All right. And you haven't seen the whole time yet. We'll see that in a few minutes. And you see whole time is considered after the clock edge. Yeah.
optic use TP. What is
Yes.
the other one called?
This is just called setup, as you see here. Setup, just setup. T setup. Yeah, that's how. Sometimes in some datasheet they will use TS and TH. H for hold, is for setup, but in many textbooks they will just spell it out. Setup. Okay. Sure. All right. So next, we're ready to see. Don't worry, we just have like two more slides left. We'll finish it today. All right. So don't worry. This can be confusing if you don't, discuss this properly. That's why I'm taking my time. Okay, so hold time constraint. Let's talk about the hold time now. Excuse me. So the hold time appears after the clock edge has appeared, like I told you, right? And we are looking at clock B. We are looking at flip-flop B. We are considering that flip-flop B needs the data well in advance. And once it gets the data, once the clock is activated, you need some stability in life. Meaning it doesn't want the input to change again because that will make it confused. Okay, so that is the hold time. After the clock edge appears, you need some time off, and that time off is called the hold time. So notice this is okay. So you have clock A and clock B here. See, once we introduce a concept, we stick to it. So we will be sticking to the skew, clock skew. Are you still with me? Okay, so you are looking at a clock A and clock B because there is skew involved. So now for flip-flop B, which clock should you see? Clock A or clock B? Quickly. Clock B. Okay. So when I define the whole time, should the whole time be before the edge appears or after the edge appears? After the edge. So that's why this is a time we just decided on a random limit. So this is the whole time for clock B. We chose this whole time. That's it. Okay. Now, notice. Please pay attention now. Imagine that while you're holding, there will be a new set of data coming at P, and that will propagate to Q, that will propagate to R again. if that appears before the hold time is finished, wouldn't that be a challenge for the flip-flop? Because before it finishes this data, it will get the new set of data already. That will be a challenge. So how can you calculate the delay for that new set of data to appear at R? You again go through the same chain. Let me erase this and put it back again. Let's see. Let's see that. So this is clock A, this is clock B. Sorry, this is the slide we're looking at. So this is clock A, this is clock B. And then for the next set of data, you go from P to Q. So you have a propagation delay, and then you have go from Q to R. So notice we don't call it propagation delay anymore. We have a new term here. And that term has been explained here, which is called a contamination delay. What is contamination delay? Okay, we haven't discussed this before, but I will now. So combinational logic, imagine you have a 3-input or 4-input NAND gate, 4 NAND. Let me just write it here. For 4-input NAND gate, you're dealing with many combinations, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, whatever. Like there are many combinations possible, right? As you know, 16 different possible combinations. And you know the output for each of them. What I didn't tell you before, and this is covered in a separate lecture in 433, is that these output input combinations don't have the same delay. Some combinations take more time to generate an output, and some combinations can generate the output fast. You see my point here? Without drawing the truth table, I'm guessing. Imagine for 0, 0, 0, 0, your output is 0. For 0, 0, 1, 0, your output is 1. Maybe 0, 0, 1, 0 takes more time to create the output versus 0, 0, 0, 0, right? And we can point, it's not random. We can easily track down the slowest possible input combination that takes the longest time to create an output. Okay? And we can also point out the combination that changes the output right away. Make sense? Or like with the lowest delay. Do you guys all understand this now? So did we ever discuss this before? No. So you see there is more to it than you have covered so far. It's not the end of digital logic. It's just the beginning. I told you this is 255, right? So apparently the truth table that you used to see, there was no time information involved in the truth table, just input, output. But what you don't know is different rows have different delays, essentially. Or different rows of truth table has different delays. So if you go through the delay numbers, whichever combination gives you the lowest delay, are you still with me? The lowest delay, that delay is called the contamination delay. Still with me? Okay. So the lowest, is it the highest delay or lowest delay? It's counterintuitive. Typically, we always care about the slowest thing because that's the worst case scenario. But for this particular definition, contamination delay is the fastest combination. The combination that leads to output the fastest. That is, that delay corresponding to that is called the contamination delay. And I'll explain why we look at the fastest one in a second. Okay, let's see. All right, so when I write CD, that represents contamination delay. Okay, now, so we assume that while your flip-flop B is trying to hold on to its own data and do some work, somehow your input changed. Your input changed, and that change has to come to Q. So there is a delay, and we are taking the minimum delay for the flip-flop. That's why I'm calling it contamination delay. I'm not just calling it any propagation delay. I'm calling it contamination delay. Okay. And then in the combinational logic, there is a delay associated with it. I'm calling it, I could have called it TP combination. Remember in the last slide, we used to use TP, propagation delay for combinational logic. That is the average value. Propagation delay is the average value. It can be faster or slower, something like that. All right. So now we are just taking the minimum, absolute minimum. What is the fastest possible way to go from Q to R through the combinational logic? And we are taking this number. Are you okay so far? And notice your combinational delay eventually brought this input change to the output. But by then, your whole time is over, don't you think? Your whole time is over. So you don't care. You can handle this. So this is the absolute edge. This is the you are working at the absolute limit of the system. So by adding these two delays, contamination delay for the flip-flop, contamination delay of the combinational logic, as long as it is linked with the whole time plus this Q, you are fine. You see that? Just look at the geometry of it. Just look at the geometry. First, tell me, is this an okay situation or not? I know it can be confusing, so I'm taking a different route. Do you think this is an okay situation for the system or not? Will the system survive barely? When will it not survive? Folks, tell me. If the delay, combination delay is lower, if it appears here, will the system survive? No, because your data will change within the whole time. It will not survive. If the delay appears higher, that means the change appears later. Will it be okay? It is even better. You have given it enough whole time to finish its thing, and then you are changing it. So it's fine. So what you don't want is the data to change during the whole time. Okay? So can I say that this is the absolute edge? This is like the system barely working. So just look at the geometry. This time period is same as the other time period. Do you see that? So just add these numbers that you look at. Delta plus T hold, which is this one, would be equal to this contamination delay plus contamination delay for the combinational logic. This is the absolute limit. But notice, do you want your whole time? Will it be better if the whole time was smaller or not? Please try to respond. It can be wrong. Do you think if the whole time is smaller, it is good or not? Yes. Thank you. Thank you. Yes. And that's what you see. I mean, just by looking at the logical flow, you can say that it is better if this thing is even lower. That will make things better. So that's why you have this less symbol here. So the total of delta plus whole time should be less or equal this other combination. Now I'm going to explain why we chose to use the contamination delay. Why you chose to use the minimum delay. Okay, here is why. Okay, imagine it, the minimum delay for the combinational logic is 10 nanosecond and the maximum delay is 30 nanosecond. Okay, if you treat that maximum delay, which is 30 nanosecond, this will appear even later. Don't you think? Will that violate the whole time or not? That will not violate the whole time. So that's good. So you have an illusion that your systems are fine. What is the worst case scenario in this situation? If the data arises too slow or fast? Too fast. If the data comes here too fast, meaning within 10 nanosecond, say here, that's where you have a failure. So you should look at the minimum delay of the system, not the maximum delay for this situation. Did I tell you in one of the lectures, the same lecture where we talked about multi-stage logic, I told you sometimes if the data appears too fast, it is a problem. I gave you an example of sending a mail to yourself at a hotel room. If the package reaches the hotel before you even check in, it will be discarded. If it reaches after you check out, it will be discarded. So too much delay is problematic. Too less of a delay is also problematic. Did I tell you about buffer insertion? The reason why we incorporate buffer, it doesn't change in input to the output, input to output, but you can change the delay. You can modulate the delay. Now, I hope you can connect. That is my target, to help you connect. I'm sorry. You know, hope you see that if the delay is too low, it is a problem. How can you increase the delay, folks? Incorporate buffer. Buffer insertion is definitely a possibility to help you with whole time violation. If you see that your data is arising too fast, you insert buffer and you push it out. Are you okay so far? So far? Okay. All right. So this is whole time. And basically, this is the last slide. I'm going to show you a violation of the whole time. And I hope you don't have to go through the chain, blah, 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 blah. The trick, use the trick. So you look at clock B. and look at the dot. This dot shows you the hold time limit. So you need to hold up to this time. Just look at the input for the flip-flopper. Is the input changing during the whole time or not? Is it changing? Do you like it? No. The flip-flop will not like it. So it is a violation. Simple. Okay? All right. Before let's see the slide before. This is your clock edge for flip-flop B. You don't look at clock A because you look at the corresponding clock. And this is your hold time. Let me draw it, exaggerate it a little bit. This is your hold time. And then your input changed right after the hold time. So you're fine. If I show you that the input changed here, you'll be even better. That's fine. I hope now you can understand. Going beyond these equations, because the equations are confusing. When I was a student, I was confused, really confused by these two equations. But they're used to write codes. You don't track these edges manually. There are like trillions of clock edges, honestly. I'm not making it up. There will be trillion. If you have a gigahertz, that is a billion clock edge. Do you agree with me? If you have gigahertz clock, that is a billion. Giga means 10 raised to 9, which is a billion clock edge. So, and you don't just have one cycle, right? So basically you have trillions of clock edges. You cannot manually do what I'm doing here. Hey, see if the clock is following blah, blah, blah. It is impossible. You write codes and you write codes based on the constants that I showed you. And that needs, codes need equations. And these are the equations. You set constraint to the system and system goes through the design and checks for every clock edges. If there is a violation for either setup time or hold time, it adjusts the system accordingly. What are your options? Change the combinational logic, make it multi-stage to increase delay. Insert buffers to increase delay. Make it lower stages to reduce delay. Or if you cannot do anything, increase the clock period. You see my point? So all of these will be done cyclically by a computer. We humans cannot handle this. That's why it's called CAD, computer aided design. In fact, okay? So that is the endpoint. I hope by now you see that it is simply impossible to keep track of these systems manually. All right. So we finally managed to finish this lecture. Thank you for your patience, and we'll move on to something new in the next class. All right. And if you're confused, please don't hesitate to come talk to me during my office hours. My office, some of you don't know when the office hour, I posted it on the syllabus. It is Monday, Wednesday, Friday, 10 to 11, but that is just a placeholder. You can find me other times as well, okay? Just send me an email or knock on my door. I'm mostly there in my office, so it should be okay.